Hey everybody, this is my Physics 2211 Lab Report 1, Constant Velocity. So this is a brief table of contents to show what we're going to be going over today. What is the purpose of this lab experiment? We are going to be creating an experimental model wherein an object has constant velocity, and then we're going to create a corresponding computational model to compare results. The computational model will have true no net forces, and thus will be a very accurate depiction of that simulation, whereas the experimental model is in Earth-like conditions and may not reflect that. These, when accomplished, will demonstrate the following physics principles: Newton's first and second laws of motion, velocity update formula, and no net forces effects on the system. First, we're going to delve into Newton's second law, the momentum principle. Newton's second law states that net forces are equal to change in momentum over change in time. In other words, the change in momentum over the change in time are directly influenced and caused by surrounding forces. This leads us to create the momentum update formula, which is that the final momentum is equal to initial momentum plus net forces multiplied by time. And if you divide both sides by mass, which you can do because momentum and net forces have mass considered as a part of their units, then we are given the velocity update formula, which is v final is equal to v initial plus acceleration multiplied by time. Change in time. My chosen system was a globe stress ball, which you can see on the right, and the surroundings were everything around the ball, including the table and the air around it, as well as the Earth. For this model to work, we have to make a couple potentially incorrect assumptions. One, that no forces are acting on the ball, so no friction and no force of gravity, which is obviously not going to happen in a simulation on Earth. And then that the ball is moving in a straight line in one dimension. Now, the table we used eliminates one dimension, but the ball could easily be moving side to side as well as forward, and so it could still be moving in two dimensions. And ultimately, we're going to find that those maybe did play a role in our findings in the experimental model. This was our experimental design. So I recorded a video of a ball rolling across the table and then used the tracker application to track its movement. And that gave us a table of values, which you can see here on the right. And then I copied and pasted that into Excel to create a graph and compare it to our computational model. Here's some important findings from the experimental model. So, on the left, you can see the initial position and final position as tracker found them. And because final velocity and initial velocity are equal, they're assumed equal because there's no net forces acting, which means there's no acceleration, then V final is equal to V initial, which is equal to V average. So V average is the change in position over the change in time. And so ultimately we found that V average is 0.3838 meters per second. And that is also equal to V final and V initial, assuming that there are no net forces. So this was our glow script model that we used. So I had to plug in some values. So I plugged in initial position and initial velocity, which we found on the previous slide. We also plugged in t equals 0.4, which is when tracking began, and delta t, which was determined by the 30 frames per second frame rate. And then I also plugged in the velocity update and position update formulas. This was the model created by the computational company. And I copied and pasted these values and compared them to the experimental model's values in Excel to create the graph. So, this graph shows that the computational model is fully linear and there's no variance off of the trend line, whereas the tracker model does have some variance, right? You can see that position between each time increases compared to computational model and then decreases, which indicates that velocity might be decreasing over time, which caused the experimental model to increase and then decrease back onto the computational model. Some possible errors were that point masses were not in the exact middle of the ball every time, and that gravity or friction acted against the ball, causing it to slow. So let's discuss this. So constant velocity is very difficult to replicate in Earth-like conditions. We have gravity, we have friction here, and external forces likely played a role in the experimental model varying from the computational one. Now, I decided to take instantaneous velocity at the beginning and at the end of the model. So v of 0.433 would be the first and second time points, and then v of 2.167, the instantaneous velocity at the end, would be the last two time points. And I found that between the first two time points, the velocity was 0.518 meters per second. And between the last two, it was 0.359 meters per second. So my suspicion was proven correct, and velocity was decreasing, which is not going to happen if we have no net forces, so that shows that the experimental model did not, in fact, reflect no net forces. What if, and what does it mean? What if the x-axis was reversed? If the signs on the x-axis were reversed, that would mean the ball were moving in the negative x direction, And the graph would look pretty much the same except rotated about 90 degrees clockwise, so it would be negative instead of positive. And what does it mean when there are no net zero forces? Many forces must cancel out to achieve net zero forces on Earth. For example, gravity has to cancel out with normal force, and friction has to cancel out with applied force. This is best depicted in a free body diagram, which is in the bottom right. And that's what the computational model calculated, but it's not what our experimental model calculated. I hope this helped you learn a little bit about physics. Thank you.